Okay, this unit is on logarithms, and to be able to do that, we need to be able to do the exponent rules, because logarithms are the study of exponents. So here are the exponent rules that you need to know. Anything to the 0 is equal to 1. X raised to the m times x raised to the n is add the exponents. If you do division with the same base, subtract exponents. If you have an exponent raised to another exponent, multiply those two things together. If you have x to the negative m, that's the same as 1 over x to the m. If you have a fraction to an exponent, you can apply that exponent to both the numerator and the denominator. Give myself a little space, and we can continue. If you have a fraction to a negative exponent, there's a shortcut for this because it's combining together the two previous rules. Essentially, you can flip over the fraction and apply the exponent to both. If you have two numbers or variables multiplied to a power, you can apply that to both of those numbers. And an often forgotten rule is if you have a base to an exponent and it equals the same base to another exponent, that is only true if the exponents are equal. And kind of a neat thing in math is you'll see the statement if and only if sometimes gets abbreviated to IFF. It's just a little aside for you. So with this last statement, we can go and solve some pretty interesting questions without even having to learn logarithms. It won't be until we get to some more complicated ones that we'll need some of the log rules as well. So let's take a look at a few examples. So in the first one we'll have 4 to the power of x minus 1 equaling 8 to the power of x minus 2. Now it doesn't look like we have any of the rules above that can help us with this. However, this last rule can help us. Right now we don't have the same base, but 4 is the same as 2 squared, and 8 is the same as 2 cubed. So you can change this 4 to 2 squared to the 4x minus 1, and this 8 to 2 cubed to the x minus 2, and then we have a rule that if x to the m to the n, you just multiply the m and the n together. So this becomes 2 to the 8x minus 2 and 2 to the 3x minus 6. And now I can use that rule because the bases are the same. So 8x minus 2 and 3x minus 6 have to be equal. Give myself a little room by working over here. 5x is equal to add 2 and add 2, negative 4, and x is negative 4/5. You can go ahead and check this. Just get your calculator out, plug in negative 4/5 for x on both of those equations, and see if the decimal place is equivalent on the left and on the right hand side. And that's a numerical check, back like we did in the trig section when we were checking proofs. Okay, so here's a second one for you, and if you'd like you can go and try and simplify this next one without, just pause the video and see if you can do it. 3 to the 5th is equal to 9 to the 2x plus 4. So if you want, go ahead, pause the video, see if you can do this one by yourself. And I'll go ahead and do the answer in just one sec here. 3 to the 5th is equal to 3 squared to the 2x plus 4. That means 5 would have to be the same as 4x plus 8. Or 4x would have to be the same as negative 3. And so x would be negative 3/4. We can also use exponent rules to simplify equations. So let's take a look at that next. So to simplify this, I need to make them have the same base. So this 9 needs to become a 3 squared. Basically, all of the exponent rules work only if you have the same base, and certainly for simplification, that's almost always true. So this top part becomes 3 to the 2x plus 1, and the bottom becomes 3 to the 2x plus 8. And now I can do subtraction. So it's 3 to the 2x plus 1 minus 2x plus 8. And the 2x's cancel, and 1 take away 8 is negative 7. And you can go and calculate what that's worth if you want. I like just stating it as a positive exponent, 1 over 3 to the 7th. Okay, the next section is going to take a look at what the graphs of exponential functions look like. So first of all, there are some restrictions. A always has to be bigger than 0, but A cannot be equal to 1. So with those restrictions in mind, we can go and see what the graph of these things look like. So for our first graph, let's take a look at what happens when A is bigger than 1. So A has to be bigger than 0 and it can't be 1, but A could be bigger than 1. So first of all, let's look at that. Well, A bigger than 1, I'll give you an example, something like 2 to the x. Okay, if it was 2 to the x and x was 0, then it would go through this point here 1 unit up. In fact, they all go through the point 1 unit up. When x is 1, it would be 2 to the power of 1, so at 1 it would go up 2. Well, I won't say what my scale is, but at 1 it will always go up a, and at 0 it will always be worth 1. And as I move to 2 and 3 and 4, this graph quite quickly goes up to infinity. On the negative side, I now get negative 1 and negative 2 for my x values, and negative is the fraction, so it becomes 1/2 and 1/4 and 1/8, and what happens in this direction is I end up with an asymptote. Okay, so that's what the basic graph looks like. Let's take a look at the other option, which is what happens if it's bigger than 0 but less than 1. Well, if it's bigger than 0 and less than 1, it still has this form, y equals a to the x, but I'm talking something like 1/2 to the power of x, or 1/4 to the power of x, or 3/4 to the power of x. So it still has this form, but now those are fractions. And if I put in a 0, well, anything to the 0 is still 1, so it still goes through the point 0, 1. But now when I put in 1, it was a fraction, so fraction to the power of 1 is still a fraction. And that's going to be true for all the fractions in this direction. In the other direction, it's going to go up. And you can see that it looks like it's a reflection, and in fact it is. But it still has the same asymptote. So if the base is bigger than 1, the graph gets bigger and bigger and bigger as the x values increase. If it is less than 1 but bigger than 0, the graph gets closer and closer and closer to 0 but would increase on the other side. And we'll see later in this unit where these are used in real life, some of the actual applications for these as well. Right now I'd like to go and see if we can remember how to use some things from Unit 1 on transformations to graph or at least sketch graphs with some transformations in them. So let's see if we can sketch 3 to the x minus 1 minus 2. So the base graph is f of x is equal to 3 to the x, and then the x minus 1 means the graph is 1 right, and this minus 2 means that it's down 2. So normally the graph goes through here, and at 1 it goes through 3, at 2 it goes through 3 squared, which is 9. So this graph goes up super quickly, but I've got a couple coordinates in here that I can use. But then this entire graph is moved 1 right and 2 down, so this asymptote moves down by 2. So it's nice to pencil it in. That's y equals negative 2. And all of these points move down 2 and right 1. So I'll draw the final graph in black. If this goes down 2 and right 1, it ends up here. If this goes down 2 and right 1, it ends up here. If this point goes down 2 and right 1, it ends up here. And these ones are still going to be an asymptote along here. And now I just connect the dots with a similar looking graph. And to be good, I should plot what these exact coordinates are. 1, -1, 2, 1, and 3 looks like it's up 7 now. So we do need to remember some things from the first unit to be able to do some things in the current unit. Okay, let's take a look at two word problem applications of exponents that you should be able to do. They do involve some new formulas, but they're not too difficult.